Questions I've been asking myself are as follows. I mean, as an earth scientist, I think a lot about the physical earth and how it's changing, um, especially from climate change. I'm a climate scientist, but also due to human environmental impacts. As a geographer, I think a lot about how humans make the earth their home. And there's really a fascinating progression there. If you look at the history of humanity, um, there's a fascinating progression of a seeming separation from nature that goes back 10,000 years and is still happening in an accelerating way today. So bear with me for a second. If you think back to the earliest civilizations, which really got going around 10,000 years ago, their origins even earlier than that, um, they formed along the river banks of the Tigris-Euphrates rivers in present-day Iraq. They formed along, even before that, along the Indus River in present-day Pakistan and India, and the Yellow River in China. And a little later, even here in North America, pre-colonial discovery, they formed along the banks of the Mississippi River with a long forgotten Native American civilization called the Cahokians. And the Cahokians had earthen and log pyramids. They had a vast empire spreading up and down the Mississippi River Valley. They had trade, administrative centers, and so on. And as fascinating as those civilizations are, they marked a big change from what preceded it with hunter-gatherer groups. And the discovery of agriculture in these hydraulic civilizations along rivers created some of the first big inventions from society. The creation of the city-state, the creation of a ruling class, the creation of some of our earliest human institutions, like engineering, science, and law. They can be traced back this far. And that was the first big step, was the removal of our dependence on foraging for food and being able to survive in fixed settlements due to irrigated agriculture. From there, we moved to trade. We discovered machines, industrial revolution. Uh, from there to global food production, and our most recent trend, which has been going on for well over a century, which is urbanization, with this incredible movement of people from rural areas to the countryside, or rather from the countryside to rural urban cores. In fact, a little over a decade ago, in 2008, a remarkable threshold was surpassed with regard to this phenomenon. Somewhere on Earth, a baby was born. We'll never know exactly where or who it was or exactly when it happened, but somewhere on Earth, a baby was born, and we crossed the threshold. For the first time in the history of the human species, we became urban in the majority. Never before had this happened. And certainly, well over half, uh, by that time, a decade plus ago, well over half had long since forgotten how to feed themselves, how to obtain water, how to um, get clothing. They had long ago ceded these most basic of biological requirements, to our organized society. And today, in the modern world, we rely very much on the efforts of global supply chains and multinational corporations to provide um, our these most basic of biological services to us, the urban consumer. So I recently moved to New England from Los Angeles, and in LA, there's a very popular food chain called Trader Joe's. sure many of you know it. Um, and Trader Joe's is super popular with Angelinos like myself. It espouses fair trade principles and fair trade coffee and great labor practices and good benefits for their employees and so on. It's a wonderful company. And many of my fellow Angelinos love to shop at Trader Joe's and gasp in horror at a Walmart, right? Which has slightly different philosophy with regard to its labor practices and so on. But the difference between these two companies is far less than they would appear, certainly to my neighbors. And both of them are reaching out around the planet to obtain goods and food items in this case and finished goods as cheaply as possible, and to route them via tightly scheduled global supply chains to us, the urban consumer. Um, they're doing the exact same thing in terms of the business model. And this model, most recently, which has really gotten going since the 1970s, is but the latest chapter in humankind's ongoing redefinition of its relationship with the physical earth. It began with our move from hunter-gatherer species as a hunter-gathering foraging species over 10,000 years ago to settled communities. From there, we consolidated more and more in cities. We invented machines to do our work for us. This accelerated the departure of people from landscapes. We went from an agricultural civilization to an urban one. In the US, less than 2% of the population is engaged in agriculture today. The fields are devoid of humans and mowed by autonomous heavy machinery guided by GPS. The advent of trade, first locally and then globally, has redistributed the way materials are circulated around the globe. Our move to a global food model only accelerated that. And now the trend has been very much to concentrate in urban cores. So while the world population is still growing, rural areas are either, for the most part, depending on where you look, of course, are in many places the populations are either stable or actually depopulating and losing people. And depending on what happens with the remaining, the land that's left behind, um, this can sometimes be good for nature with rewilding of forests and the return of species that have been extirpated there from the past. I mean, a wonderful example of this is all around me here in New England. This is a landscape that was, of course, at first dammed up everywhere. Every little river and stream of any substance was dammed to make mill races for the Industrial Revolution. The forests were cut down. The whole area was covered with hardscrabble farms and pasture. Uh, Beavers and fish and other forms of wildlife were extirpated. Um, and now, in the year 2020, the place is regrown with thick forests. There are beavers all over the place. And while highly suburban, most of the human activities are taking place in the city with much milder impact upon the surrounding local environment than has happened in this area for hundreds of years. Of course, those impacts, the environmental impacts of that urban activity are now global with climate change. This is a topic I really spend most of my time on for my day job. I'm an Arctic climate change scientist. I do a lot of work in Greenland and Siberia, and northern Alaska, and so on. Looking ahead, I wonder a lot about how this changing relationship between humans and the physical earth will continue to change. I wonder if we will burn the remaining reserves of fossil fuel, which is the track we're currently on, or will we leave it in the ground? I wonder if we will defend our coasts from sea level rise, or if we will retreat from them. If we do, and I wonder if we do retreat, what will be the nature of that retreat? Will it happen in an orderly way, or will it take major storm surge events, like we've already seen with Superstorm Sandy, for example, to render areas suddenly uneconomic or unbuildable, or has happened with Hurricane Katrina along many, many miles of the Gulf Coast. I wonder if we will geoengineer our climate. There are a number of proposals for this. The idea, in just the last 10 years, this idea, even among scientists, earth scientists like myself, this idea has gone from being, kind of an outlandish concept to one that is being taken with increasing gravitas as the national and international level effort continues to fumble and falter. To effort to slow the pace of climate change at the international level continues to fumble and falter. I wonder if humans will take control or partial control of evolutionary processes and begin to direct evolution through synthetic biology. That is, my own interest in synthetic biology extend especially to the modification of plants, modification of plants for human food, potentially the modification of human plants as a mitigator of climate change through carbon sequestration. And I wonder what the implications of this may be. I really am astounded to think what kind of life experiences my 3 small kids will encounter as they go through the next 80 to 90 years, particularly in this area of synthetic biology. I speculate that the changes they will see will be in their generation will be even more dramatic than the ones I've seen through the information revolution of the last 40 to 50 years. I wonder if we will populate the Arctic. This is a place that is continuing to warm, and not that it'll ever be warm in the wintertime, of course, it's the Arctic. The polar night will always return, but it is also a place that has a great deal of fossil fuel energy that is not currently developed. And should we stay in the path of fossil fuel development, it is an area that is likely to be accessed and used for this purpose. And we're already seeing that in places like northern Siberia, the North Slope of Alaska, the oil sands or tar sands, depending on your point of view, of Alberta and Canada, of northern Alberta. So I wonder if our long trend, lurching trend of global integration, which has its roots in the wreckage of post-World War II, beginning with the Bretton Woods Agreement, I wonder if that long, lurching global integration will stop and will reverse. Certainly, developments of the very recent years have suggested this is possible, without getting into the politics of it, but the Brexit is a prime example of it. There are many indications around the world that this ideology is maybe changing, and it is quite plausible that we could deglobalize moving forward. I wonder if the current COVID-19 pandemic could inspire, or I wonder if the current COVID-19 pandemic will either deter or inspire um, use of biowarfare. Biowarfare the most has long been the most untouchable and covert form of warfare. Been around forever. It's an old idea, of course, but has always been considered untouchable by national actors. And I would hope it would continue to be. But it is fascinating to wonder as the COVID-19 pandemic um, continues, which is the biggest experiment of its kind unleashed on civilization since 1918, over 100 years ago. I do wonder um, to what extent it could inspire biowarfare in the future, particularly along non-state actors such as terrorist groups. And finally, I wonder what, looking even more broadly, I wonder whether we might, in future decades, consider dispersing life off of the Earth. And if so, what kinds of lessons might be learned from the dispersion of life on this Earth at human hands? So those are just a few of the things I've been thinking about with all my time off. For over 25 years now, my climate change research has drawn me north to the Arctic and subarctic. These are the ice sheets and glaciers and permafrost lands and seas of Alaska, northern Canada, Iceland, Greenland, Siberia, the northernmost Nordic states. And the reason I and my graduate students spend so much time working up there through field studies and satellite remote sensing is because the Arctic is one of the most rapidly transforming regions on Earth, both from amplification of global climate change, as well as human pressures that are unique and operating within the region itself. And let's start with the first one. The Arctic, unlike Antarctica, uh, experiences greatly amplified increases in climate warming that are larger than the global mean temperature increase, and unlike Antarctica. And whenever the planet warms up by a degree on average, that 1 degree average is actually masking some profoundly different geographical contrasts around the Earth, with the Arctic experiencing well over double the global mean average rate. And the reasons for this are not mysterious. We understand them quite well. There are a number of geophysical feedbacks that operate within the region that are present in the Arctic, but not present in Antarctica, for example. The biggest one and most famous of these natural feedbacks is the geography of the region. Unlike Antarctica, which is a continent buried under very thick ice, over a mile of ice, that is very ancient, over 1 million years old. The Arctic, the geography of the Arctic consists of an ocean surrounded by land. In fact, massive amounts of land, with the largest land mass on planet found in the northern high latitudes. It's where two of our biggest countries are, Russia and Canada, for example. And the fact that there is an ocean there surrounded by land rather than a continent surrounded by ocean gives rise to what's called the ice albedo feedback, meaning the way it operates is the albedo or reflectivity of a dark ocean is much lower than that of ice and snow, which is highly reflective. And the ocean always freezes in winter, and hopefully always will, because remember, the polar regions will always have polar night in the wintertime. And so the ice, no matter how warm it gets in the summer, ice will always refreeze in the winter. And the Arctic Ocean freezes over in the wintertime and begins to melt back from its edges during the summertime, reaching its sort of minimum seasonal extent in late September. And the extent of that minimal summertime sea ice cover in the Arctic Ocean has been steadily declining ever since NASA first started mapping it using passive microwave satellites in the late 1970s. The maximum seasonal extent of ice cover in the Arctic Ocean has declined by about 40%, over 40% since the late 1970s. And this causes the reflectivity of the surface of the planet up there to decrease, because as that ice melts back, it exposes a darker ocean, which absorbs more of the incoming solar light. So rather than being reflected back to space, that energy is absorbed by the ocean, which warms the ocean water and retains heat within the system, which is then re-released throughout the year. So this is one of several feedbacks operating in the Arctic, which are unique to the Arctic and cause the place to experience amplified climate change. Now, importantly, this feedback works in the opposite direction as well. So when the Earth enters periods of global cooling, such as during ice age oscillations, and when global temperatures decrease, temperatures in the Arctic will plunge more than double the global average. So it is a highly amplified system. From a human presence and development point of view, the Arctic and Antarctica couldn't be more different. The Arctic land masses are under the political control of 8 sovereign nations. They belong to those countries, these territories and adjacent seas, namely the United States, Canada, Greenland, which is an autonomous region of Denmark, Iceland, Norway, Sweden, Finland, and Russia. Antarctica, in contrast to the Arctic, is totally different in its political organization. It is shared among nations, and the entry key to having participation is the expenditure of funds on science and maintaining science camps in Antarctica. So Antarctica is a fascinating place because many countries want to be involved with Antarctica for geopolitical reasons, but the only allowable way in which this can manifest is through the funding of science in Antarctica. So it's wonderful. As a scientist, I think it's absolutely wonderful. But the governance situation, it couldn't be more different. The Arctic, being comprised of sovereign nations, is governed by the rules of those sovereign nations, and offshore is governed by a very important piece of international law called the United Nations Convention on the Law of the Sea, which governs the offshore exclusive economic zones of all signatory nations, 200 nautical miles, and through a provision within this piece of international law called Article 76, signatory nations can petition to extend their offshore sovereignty through scientific mapping and geological studies if they can establish that the seafloor is a natural extension of that continental shelf. And it just so happens, due to the geography of the Arctic Ocean, it's a fairly small ocean and very shallow. And as a result, most, if not virtually all, of the Arctic Ocean either already has been or soon will be partitioned between 5 Arctic countries that abut onto the Arctic Ocean, perhaps even the North Pole itself. The biggest beneficiary of this is Russia, Canada, also Greenland, the autonomous region of Denmark, the United States and Sweden and Norway also have some claim to the area. So when you couple that governance structure with the extensive potential reserves of natural gas, condensate, and oil in this region, the development prospects for this remote, iconic part of the world are huge over the long term. Not in the short term. Low oil is a very, very difficult place to operate, very expensive, very environmentally fraught. Um, Many national and multinational oil companies have attempted to operate in the Arctic and have failed or have withdrawn. But over the long term, should current trends continue as they are now, and I hope they don't, but should they, there is little question that the pressures to develop the fossil fuel reserves of the Arctic and subarctic will be immense, and in fact has already begun in Western Siberia, where the decades-long oil and gas development of Western Siberia by the Russian Federation beginning in the 60s when it was the USSR have now expanded north to the Yamal Peninsula, where in 2017 the Putin administration opened up a liquefied natural gas (LNG) plant at Sibeta on the coast of the Yamal Peninsula. So has already begun there. And in North America, of course, we have the ongoing bumpy, depending on the price of oil, bumpy development of the oil sands or tar sands, depending on your point of view, in northern Canada. So the climate changes happening in the Arctic are more extreme than the climate changes even in Antarctica, which is also undergoing tremendous warming, and the development potential and pressures and governance are totally different between the Arctic and Antarctica. And this is why we see such an asymmetric sort of two asymmetric spheres of activity and interest taking place in these two very important and iconic regions. I will hasten to say, however, that the single greatest uncertainty in global sea level rise risk does come from Antarctica, which is why the reason it is under acute and scientific scrutiny and study. And this is because a large fraction of that ice mass is grounded on the continent below sea level rise, and it is also ringed by large, thick ice shelves that buttress glacial ice up on the land. And if those ice shelves disintegrate, which they're prone to do when ocean waters warm, their ability to buttress the land ice up on top of the continent goes away. If you remove the plug at the bottom, then the land ice can flow right down to the ocean. And this is quite a frightening possibility. We don't understand the processes involved very well. Our ice dynamics models are not well calibrated because we don't understand all of the tensile physics that are found along the interaction of the glacial bed with the overlying ice, and the interaction of those physics with the buttressing effect and ocean temperatures at the ice edge are they're present in the models, but our models are not calibrated well enough to really be able to know if and when this might happen. So it creates a big error bar in our uncertainty about how fast and how high sea level may rise by the end of this century. There is the sort of collective body of wisdom gets summarized every few years with the United Nations IPCC reports, which are notoriously conservative and slow in their assessments. That's understandable. It's because they're consensus documents that have to be signed off on by governments. But the most recent IPCC release, which just came out in September, has significantly upgraded their risk potential for sea level rise, to be as high as anywhere from 30 centimeters to 1.1 meters by the end of this century. And again, it must be kept in mind that this is a conservative document, and much of that, the reason for such a large range comes from uncertainty surrounding the stability of the West Antarctic ice sheet. Some of the most exciting research I'm doing, together with my graduate students and postdocs and collaborators, is improving our ability to model and predict how much sea level rise will come out of the Greenland ice sheet. And the next time you look at a world map or globe, have a look at the Greenland ice sheet and look at its latitude. And you should be struck by the oddity of it even existing at all. Here we have this massive ice sheet coming to quite low latitude, um, an ice sheet sticking up above everything else. It's really quite out of place, unlike, say, the Antarctic ice sheet, which is, perched right at the bottom of the Earth on the South Pole. And in fact, the Greenland ice sheet is a relic of the last ice age. It survives only by virtue of its own elevation. And what I mean by that is if you were to somehow magically pluck the Greenland ice sheet off of the bedrock, it would not reform and grow. It just would not come back. The reason it persists at all is because it's already there, and therefore at its higher elevations, at the summit, the temperatures, the elevations are sufficiently high that the temperatures do not go above freezing during the summertime. Just like when you get an airplane and you go up, the temperatures get cold. So there's a very strong decrease in air temperature as you move up through the troposphere. So this is what allows the Greenland ice sheet to exist. Now, it does melt extensively around its lower elevations along the margins. And so and this is the area that is ground zero for Greenland's contribution of meltwater runoff to the ocean, and ground zero for the single biggest component of sea level rise contribution from Greenland to the rest of the world, a little present from Greenland, if you will. And the extent and intensity of this melt zone around the edges of Greenland have been dramatically increasing pretty much every year, quite steadily. I mean, it's bumpy. Some years are cooler, some years are warmer, but the overall secular trend is one of increasing melt and mass transfer from the Greenland ice sheet to the ocean, where it contributes about a third of global sea level rise at this time. Over 1 millimeter per year is coming just from the Greenland ice sheet. And so my team and I have been pushing this science forward by studying this melt zone. And surprisingly, until quite recently, this area received light scientific study. Most ice sheet scientists and field expeditions focus on drilling camps up at the top in the cold zone, where, since it doesn't melt, the ice core record is preserved. And these are amazing places to drill 2 miles down into the ice all the way to the bed and pull out a 2-mile long time machine of past climatic changes over geological history. The melt zone along the edge is a real mess. I mean, it melts every summer. If you try to envision it, just imagine a vast slick and slide water park where, sure, it snows over in the wintertime, but come June, the whole place starts to melt. It's crisscrossed everywhere with torrential flowing blue streams and trickles that come together into streams, which come together into these great branching arterial river networks flowing over the top of the Greenland ice sheet. And every single one of these torrential blue rivers in southwest Greenland, which is the most intensive area where this melting is taking place, virtually all of them travel for a few kilometers over the ice before breaching through the ice into a sort of sinkhole called a moulin. And from there, it tunnels under the ice and out to the ice edge, where it goes right into the ocean, thus contributing to global sea level rise. And this is where this is where 90% of the runoff from the Greenland ice sheet to the ocean is coming from. It is so modeling this melting process and sea level rise contribution process correctly is imperative if we are to be able to forecast with reasonable accuracy the anticipated rate of sea level rise in the future. And amazingly, until the work of our group, the no testing or validation of the climate models that operate for this purpose had ever been conducted for Greenland before. So beginning in 2012 and for many summers ever since, I and my team have been helicoptering onto the Greenland ice sheet in this fantastical melt zone where we use helicopters to string cableways over the top of these rushing superglacial rivers and hang a river discharge measurement technology called acoustic Doppler current profiler, or ADCP, on these cableways, and we operate around the clock, working to collect measurements of river discharge every hour, 24 hours a day around the clock for up to a week in duration. And through these measurements, we've collected the world's first meltwater runoff measurements on top of the ice sheet. And what we then do is simultaneously use drones and satellites to map out the upstream contributing watershed area flowing to that point where we are collecting the discharge measurements. And when we know the contributing watershed area and we have the runoff, the flow measurements at the bottom of the watershed, we then have a completely independent field data set from which we can test the ability of climate models to model or to simulate meltwater runoff from the Greenland ice sheet. And it's those models that are being used to predict the future. And it's these models that are being used to estimate projected ranges of sea level rise in IPCC reports and so forth. And so the field work, of course, it's incredible. And we camp on the melting ice. We pitch tents on top of the melting ice. There's water running everywhere. The tents need to be repitched every couple of days because the ice surface is melting all around us. So wherever you pitch your tent on one particular day, that is shaded from the sun, so the ice melts around it. And after a few days, the tent is perched up on a little knoll and is tilting around and so forth. The entire camp we have to take, we of course take safety precautions very, very seriously. If anyone were to slip into one of these streams, they would be washed away because the water is super cooled. It's about 0 degrees Celsius. There's nothing to grab onto. They're just fast flowing chutes that have melted into the ice. There are no rocks, no trees, no branches. There's nothing to grab onto. And as I said before, every single one of these streams and rivers flows into Amulan, which then thunders its way down to the base of the ice sheet. So if everyone ever were to slip and fall into one of these things, they would not be recovered. So as a result, to work in this environment, it's quite possible to work very safely in this environment, but there are many precautions that we must take. First thing we do is we encircle the entire campsite with yellow caution tape, and no one is permitted to leave that small area of ice unless they are tethered into a rope. And and this is flat. This is not mountaineering. The place is just flat and crisscrossed by streams. But nonetheless, when someone goes outside that camp perimeter, they wear mountaineering harnesses and latch into a rope, which a partner then feeds out a line from. And then the scientist goes to the edge of the river where the cableway is and the ADCP and collects the measurements, towing the instrument back and forth across the river while someone else is making sure that that rope, which is really a leash, is never long enough for them to even possibly fall into the river in the first place. The rope is kept tight enough that is physically impossible. So We've been collecting these types of measurements for several years, and the publication, the findings are just now coming out. And there's I'll tell you some of the preliminary results. I'm actually working on one of the papers right now. The there's good news and bad news. The bad news is that the meltwater generated by melting across this area of southwest Greenland, unfortunately, virtually all of it escapes the ice sheet to the ocean. We were hoping to find that, yes, the ice melts, but the meltwater would be somehow retained up on top of the ice sheet. Maybe it would collect in little lakes and pools and just refreeze. Maybe it would soak into the cracks in the ice and refreeze and stay there. You know, it would be wonderful from a sea level rise point of view if the meltwater that is produced by warmer temperatures over the ice would somehow remain or be trapped or refrozen within the ice sheet itself. In such a case, we might expect the ice sheet to lower, but also become denser and not lose all of the mass to the ocean. Unfortunately, our satellite mapping and measurements confirm that this is not the case, and that the surface of the Greenland ice sheet is amazingly efficient at losing all of the meltwater that drains, that forms on its surface through these networks of hundreds of rivers flowing over the ice. That's the bad news. The good news is that in study after study from our measurements, we have shown that the current generation of climate models that are used in this area are almost without exception overestimating the amount of meltwater that is produced by, on the order of sort of 10, anywhere from 10 to as high as 50%. That's good news in the sense that some of the direst predictions of runoff contributions of sea level rise or to sea level rise from Greenland are a little too high. And we're digging right now into the reasons for this. It may be one possibility is the models are overestimating for reasons pertaining to energy balance. The other more likely reason is that some of the water is indeed being trapped within a sort of rotten zone. It's called rotten ice on the top of the ice surface. It's a very fragmented, porous, rotty looking ice that appears to be storing and retaining some of the water. But finding that missing fraction of overestimation is what we're working on now. But more generally, the take-home message is that it is both exciting and scientifically critical to get boots on the ground into the field to test and verify these climate models, which are becoming of course, an increasingly critical tool for us to plan and project and to plan for the future. Yet I had always been interested in snow and ice and rivers, in no small part due to my dad, who is a very highly respected earth scientist. And we would spend our summers in the Canadian Rockies visiting his field sites, and he was interested in the actually meltwater streams and rivers draining glaciers in the Canadian Cordillera. So in the summer times, we would pack up the station wagon with my brother, our dog, my mom, and my dad, and drive the thing from downtown Chicago, where I lived a very urban, gritty downtown life, up to the Canadian Rockies, where we would camp and live in cabins for a couple months out of the year, doing scientific fieldwork around these beautiful meltwater streams and lakes and rivers in the Canadian Rockies. So that had always interested me. And when I, after a one-year stint with the U.S. Geological Survey, after my master's degree, when I rediscovered that I liked school even better than the regular hours of a 9-to-5 job, I applied to Cornell University's Earth Science Department and began a PhD there. And it was at Cornell in the Earth Sciences Department where my real transformation as a scientist began. First, there was the access at an institution like Cornell, the access to really big minds and thinkers and it becomes an everyday occurrence through, for example, through guest lectures and colloquia from eminent visiting scientists. And uh, Richard Alley was visiting Cornell to speak about his latest work, which had just come out in Nature, which used ice cores from the Greenland ice sheet to show how global climate, or more specifically, North Atlantic climate, at the end of the Younger Dryas cold snap, which was a, a brief relapse into ice age temperatures that happened just as North America was as the world was pulling out of the last ice age. It was warming up, and suddenly, almost instantly, the ice core record showed that the temperatures dropped, plunged back into cold, ice age type temperatures, then stayed cold for a while, then warmed, cold, warm, cold, warm, cold, and boom, jumped out and continued on its warming trend. And so the temperature swings were dramatic, on the order of several degrees, happening in a couple of years, perhaps even within a single year. It was absolutely astounding work published in Nature. And Richard Alley was the lead author of that work and a very famous person. He came to Cornell, he gave a lecture on it, and then, as is customary with these types of academic visits, there was a sign-up sheet to meet with him, and even lowly graduate students such as myself were permitted to spend 30 minutes with him talking about whatever. So I nabbed one of those spots with Richard, and was prepared, very much looking forward to hearing him talk about himself and his discovery and how he got there and so forth. And to my amazement, he didn't want to talk about any of that. He insisted upon talking about me and my projects and what was I working on. And at the moment, I was working on something which was very hot at the time called wavelet transforms. It's a mathematical tool, mathematical filter for time series analysis. And um, I was almost embarrassed to talk to him about it, but he pressed and insisted. And before I know it, I mean, we ran over time. He was late for his next appointment, and we had just had this very stimulating, exciting conversation back and forth. So what I learned from that encounter is that, many of our greatest scientists are just perpetually curious. It doesn't matter who they speak to; they're always hungry to learn, always excited to hear new ideas, and interested in engaging and discussing them more than talking about their accomplishments, which was just fantastic. Um, the other formative experience I had at Cornell was running into the culture of that earth science department, which was founded by, not founded, but the earth sciences at Cornell at that time was populated by some towering giants in the field of tectonics, including my own advisor. His name is Brian Isaacs. He and his advisor, Jack Oliver, at Lamont Doherty Earth Observatory, which is part of Columbia University in New York, discovered plate tectonics in the 1960s. And when I say discovered plate tectonics, what I mean is that Brian, then a graduate student, and his advisor assembled the data sets that made it all come together and collected some of them and assembled them and finally stitched together, pulled together the pieces of the puzzle that revealed the existence of plate tectonics on Earth. And they saw the data set, the main data sets they looked at were magnetic reversal stripes, which have matching sets on either side of spreading ridges in the ocean, and the epicenters of earthquakes. And the story, as I heard it told, was that Brian Isaacs and his advisor were standing in the advisor's office at Lamont Doherty in New York and sketching on a blackboard with little X's the locations of the epicenters of earthquakes near what we now know to be a subducting zone where one piece of continental crust is plunging beneath another. And Brian and his advisor, Jack, were I wasn't there obviously, but as I heard the story told, were plotting these little epicenters, little X's, and then they were going down, down, and down, and down, and puzzling and musing over these. And then Brian, suddenly blurted out, "It's going down. The crust is going down. One is getting dragged beneath the other." And at that moment, it all finally became clear that the Earth's crust was being born at the spreading center ridges in the oceans, and the magnetic reversals were capturing that slow growth over time, and then they were being subsumed and plunging on the other end in the death zone, where one plate was subducting beneath another. They arrived at this idea mutually. They flipped a coin over who would write the paper, or who would be lead author on the paper. My advisor, Brian, won, and he got to be lead author on it, but the lead author on the paper that put together for the first time the theory of plate tectonics, which launched a revolution in the earth sciences that is still kind of in the mop-up phases today. The benefit to me from working at Cornell was that because of this legacy with Brian Isaacs' works and also Jack Oliver, because both Jack Oliver and Brian Isaacs then moved to Cornell University to the Earth Sciences Department, and they brought with them a whole cohort of big thinkers in plate tectonics who, for the first time, were really looking at the Earth at the very, very broadest possible scale to get big picture understanding of the Earth system, and by its very nature, plate tectonics demands that kind of perspective. So when I arrived there in the 1990s, I brought with me a very small field-oriented mindset, where I wanted to take a very small watershed and study it and understand all these detailed little processes. And my advisor and committee there pretty much beat me up over that and said, "This is Cornell University. We think big. We think big. We think big. You have to broaden yourself out." And so that was the beginning of my sort of transformation from thinking very small about the earth sciences and the wonders that it entails, all the wonders that it entails, to also try to step back and to gain very broad scale theoretical and observational knowledge of the Earth at the largest possible scales. And this is one reason why I now work. My research spans everything from sort of broad Arctic change to societies, and to the humans and the way we make the Earth our home. The other very influential person on my career was a colleague at UCLA in the geography department, named Jared Diamond. Jared Diamond was enormously influential on me. First of all, I had, well, the story goes like this. My first or second year at UCLA as an assistant professor in the geography department, I was put in charge of the moribund colloquium program, which had few speakers and no one would attend the talks. I was told I had to revive it and that there was no money to bring in speakers. I had a budget of $0. I said, all right, UCLA is a pretty good school. I think there are some good speakers here. Perhaps we could invite them to the geography department to speak to us. So I had heard of Louis Ignarro, who had just won a Nobel Prize in medicine. And I had heard of Jared Diamond, who at that time was in the medical school at UCLA. I rang up both of their offices and reached their administrative assistants, left messages with them. A few days later, the administrative assistant for Louis Ignarro called me back and told me, yes, Dr. Ignarro would be delighted to speak to the geography department. There would be a speaking fee of $10,000. Around the same time, Jared Diamond called me back personally and said he would be delighted to speak to the geography department, period. So we scheduled him And a few weeks or months later, he came and gave a talk based on guns, germs, and steel. And the book had either just come out or was just about to come out. And many of the ideas in that book are highly geographical. The talk was great. The faculty hung around for what is probably the longest Q&A session I have ever witnessed. Went for about 45 minutes. Fantastic back and forth between Jared and my colleagues. He had a wonderful time. We had a wonderful time. And a few months later, we got a query from Jared about the possibility of transferring to the geography department at UCLA. So I was not part of those discussions. I was just a starting assistant professor, but I like to take some credit for enticing Jared to geography at UCLA and leaving the medical school. Jared left me alone until until I got tenure, and I established my core research working with field studies and remote sensing in West Siberia, Iceland, Alaska. But after I received tenure, he really encouraged me. Once again, a influential person on me encouraged me to think a little more broadly, even beyond the hard earth sciences. And I had read Jared's books. I was very inspired and excited by his synthetic way of thinking. I really value the way he looks across different disciplines and tries to find common threads and pull them together, and is does not hesitate to learn from other fields, even if they're a bit far from his core academic research. So that has inspired some of my own efforts with my own writings outside of my core science. So I would really say those two individuals were extremely influential upon me uh, along this academic career and intellectual career that I'm still on. I look forward to meeting the next person.